Okay, don't know if anyone's watching or if you can all hear me. But as you can see, it's just about to get dark here in Germany. And so the plan is to photograph the Sunflower Galaxy using my telescope. Now it's a very distant target. It's 30 million light years away. So I expect to have to take... I don't know if anyone's watching or if you can all hear me. I expect it will take an awful long time. So I'm planning on about 4 hours of imaging time for this galaxy. So let's see how it goes. Alright, so first of all, you can see the telescope here. It's popped right now. But most importantly, the cover is still on. Let me take that off first of all. There we go. And I also want to turn the mount on. Otherwise we're not going to get very far. Alright. Now it's not quite dark yet. But you never know. We can see, the next thing I want to do is to get the telescope oriented so that it knows where it's pointing. So I have a computer here which can drive the telescope. It has all the necessary programs, so let's get those started. And there we go, start it all up. And this program here is kind of like a remote control for the telescope. There we go. So let's unpack it. Alright, and so now the telescope should be able to move. Yep, there it goes. Now, yeah, I'm starting to see some stars, so we can see the bright stars right now. So we could try and get this telescope oriented. Now, I could go and use this viewfinder here and try and point the telescope manually at all kinds of targets. But I have a better way, which is to use this program here to actually take some pictures, some test pictures of the sky, and then match those to known stars in the sky so the telescope can orient itself. So that's what we're going to try here. So let's connect this program to the telescope and to the camera, which is here. There we go. That's all connected and it's starting to cool down. Very nice. Alright, so let's do just a test exposure here. Of course, right now, as you can see, it'll be a picture of the roof, totally out of focus. So don't expect too much from this picture. There we go. It's just to judge the light levels, and as we can see, it's still pretty bright. So we'll want to bring that down a bit, maybe something like that. It's a little exaggerated. How about this? Not quite sure what's going on there. Yeah, so it's either overexposed or completely black. Whatever. Let's try and point the telescope somewhere. So what we want to go for tonight is the Sunflower Galaxy. And the Sunflower Galaxy, let me show you here in a simulated view. So this is a program called Stellarium, which shows me what the sky looks like right now. So this is pointing directly east, which is over there. And so there's a bright star which you probably can't see on the video, which is almost directly east, and that's Arcturus, which you can see right here. Now the galaxy that we want is the Sunflower Galaxy, is out here somewhere. Let me show you. So Sunflower Galaxy. Yep. So if I go from Arcturus up to there, to the Big Dipper, I can see Alkaid. Actually, it's up there. So the Sunflower Galaxy is somewhere up there. And so what I want to do is find a bright star which is relatively close to the galaxy, so we can get oriented. And so I think this is a good star. This is Alkaid, which I can see already. It's up there. And so the telescope ought to be able to find that pretty easily. And then once it's found that, it can then slew over to the galaxy, which is pretty close. And so let's go and find that star first. All right. So let's move back to this view. Here we go. All right. There we go. So let's go to that star Alkaid. So it's more or less pointed towards the North Pole. This axis is pointed towards the North Pole. So it's going to make a best effort to go and point at Alkaid where it thinks it is. But of course it probably won't find Alkaid immediately because it's not aligned, and so that there'll be a small deviation to do. But so it's pointed where it thinks Alkaid is. And now we're just gonna let him take a picture. Now again, that might be overexposed. Yep, that's a disaster. He's not gonna be able to resolve anything there. Okay. So let's bring the gain down. Yeah. What does that do? Yeah, that's quite a bit better. So you can see there are some stars here. So this is going to fail because that first image was much too high exposure. So yeah. You know what? Let's just start again. Do you want to? Yep. Always happens in a live stream. All right. So let's start that camera program again. There we go. Connect to all equipment. There we go. That's all connected. And so let's go to that star again. Now it should be pretty much on there already, but he should be able to take an exposure and find out where he is on the sky. That's much better. Yep, so I figured out where it is. And I don't know if you heard or saw that. So the mount moved just a little bit. We can see here 53 arc minutes, which is 1 degree. So we're 1 degree off, and so hopefully now we should be looking at that big bright star over there, which is Alkaid. Yep, there it is. That's Alkaid. Nice. So what we're going to do now is focus the telescope. This is kind of focused, but it's a rough focus. We want to get it exactly focused so that we get the best possible picture of our galaxy when we move over to it. So I'm going to zoom in really deep, really closely onto Alkaid, like that, and start a loop here. And so that's just gonna, in a continuous loop, show me the star. There it is, every second. And I'm gonna make the camera a bit brighter so that we can bring this exposure down. There you go. And so now we see repeated imaging of that star, Alkaid. And so to find focus, well, there are a number of things we can do. We can try the old-fashioned manual way. So I have a focus motor on here on the telescope, and so that's going to move the mirror in this telescope forwards and backwards. And so I can drive that motor with this program here. start it up. There we go. Okay. So I can now control the position of that mirror using this this program here, and I can look at the star at the same time. So let's see what happens if I move out, say, 50 units. And so I'm going to watch this star closely and see if it gets bigger or smaller. We want it to get it as small as possible. Did you see what happened? I think it got a little bit smaller. So that probably means we're going in the right direction. Let's try another one. See if it gets bigger again. No, it didn't budge. So probably somewhere in between there. So let's go back a bit here, somewhere like that, and then say 30220 something. So this is clearly out of focus, as you can see, because it's much too big. So let's go to where we think the focus was, which was about there. That's kind of the smallest that I could get that star. But I have another trick. I can use this. This is called a Bahtinov mask. I don't know if you can see it. So there are grooves in one direction here, and then grooves in a different direction at the top there. And if I put that on the front of the telescope, there we go. And I'm going to have to move it a little bit because my star is, that's because I was walking around, so I've you know, very, very slightly moved the focus of the telescope. So let's try and get that back in view here. That's the wrong way. Let's go the other way. There we go. And now you can see these spikes from the Bahtinov mask. And what I want to do to get the focus absolutely right is I want this line, this center line, to be exactly equidistant between these two diagonal lines. And as you can see right now, it's pretty close, but it's not exactly. It's a little bit too far to the bottom. So let's see if we can make some fine adjustments to the focus to get that even better. So I think this, yeah, we're going to have to do this again. Scan ports, yeah, okay, never mind. Can ignore all of that. Alright, so that was our value. So let's go out by a very small amount, say 10. And see if this line here goes the right way, which is up, or the wrong way, which is down. I think that line moved up, so let's try it again. That would mean that we're going the right way. Nope, we're going the wrong way. Alright, so let's do our trick from just now again. And approach. You always want to approach from the top, because what we want to do is to push the mirror up against gravity. We can adjust the focuser by moving the mirror down, but it'll be a lot less accurate. So that's why I always rewind out of focus with the mirror far too far down and then move it up to the right position, always in the same direction. Okay, so let's go back there and then do our focus. Yeah, so you see now it's far too far up towards the top, so let's try and bring it exactly in the middle. Getting there. That's pretty close. I think it's even a tad too far, but the previous one wasn't, so it looks like the good value is 30205. So let's try that. Let's go deliberately out of focus again, and then 30205. So how's that? That's pretty much in focus. What do you guys think? I think I'm gonna add 2 just for luck. Yep. That looks good. Alright. So let's stop this loop and take the Bahtinov mask off again. So yeah, this was invented by a Russian photographer, I think in 2002 or 2003, something like that. And it's a brilliant device. It's really simple. So it slits in one way and slits in the other way, and they cause these diffraction lines on the image, which you can see here, and which allow you to achieve perfect focus. So that's great. So let's zoom all the way back out again and take another preview just for the hell of it. See how much darker the sky has become. Yeah, there we go. So that's Alkaid. And there's a bunch of other stars, much dimmer stars, which we can't see with the naked eye, which are close to Alkaid. Alright, so remember that what we want to do, let me go back to the stellarium here. What we want to do is not photograph Alkaid, but we want to photograph the Sunflower Galaxy, which is very close to it. Oh. Sunflower Galaxy, there it is. Yep. So that's our target for tonight. Now we need to plan things a little bit. I want to take 4 hours of exposure. So what I want to do when I move the telescope over to the galaxy is I want to make sure that it stays absolutely dead centered on that galaxy for 4 hours straight without moving. And as good as this mount is, I mean, it's pointing more or less to the North Pole, but there are obviously a few errors, and this motor in here, which turns around the telescope and tracks the galaxy, is not perfect either. So we're going to need some technique to actually adjust the errors in the mount and in the pointing, and maybe in the seeing. If there's a lot of atmospheric turbulence, then stuff can get bent and jiggled around in the sky as well. And so we're going to use a technique called autoguiding. So let me first take this view and the camera. So this is a feature in this simulating program, Stellarium, which allows me to see exactly what the galaxy will look like in my picture. Now, unfortunately, I did something stupid. Okay, let me start Stellarium again. 1 second. Alright, can you guys still see Stellarium? I think you can, right? Yeah, looks like you can. Alright, so back to Stellarium. Go back to the Sunflower Galaxy. Flower Galaxy, that's the one. Okay, and there we are. For some reason I blended out all the stars, which is obviously a terrible idea because I'm going to use the stars to keep my telescope pointed in the right way. Now, this is kind of the orientation. So let's zoom out a bit and show you the equatorial grid of what's happening in the sky. So everything in the sky, it looks like everything in the sky is rotating around the North Pole, which is here. So my galaxy is going to move around over there, which means it's going to move around kind of in that direction. And it's going to turn while it does that. It's essentially it's going to follow this North Pole around. Of course, it's not the galaxy that's turning, it's the Earth that's turning. The Earth is turning that way, and it's turning around the North Pole. So, but this shows me what it's going to look like in the camera. Now this is a bit confusing. Let's turn this grid off again. This is a bit confusing when I'm planning things out. So I have a feature here in Stellarium. If I know that I'm using an equatorial mount, one which takes out the Earth's rotation, like I'm doing, then I can just tell Stellarium to rotate its view. And as you can see now, it's actually going to keep the sky fixed so that I can plan things more easily. And it's going to rotate the Earth. So if I, let's say I simulate what happens further during the night, you'll see that the galaxy and the stars are actually staying in place in Stellarium, but the Earth is moving. And so that's what I'm going to use to do my planning. Now let's go back to right now. And so here you see the main camera, which is this camera, which is going to take the pictures of the galaxy. And to keep the galaxy exactly steady, to keep the entire field of view steady, what I'm going to do is I'm going to take I have a second camera, which is this one, which is mounted to the side, and the effect of that is going to be to take another picture which is some distance off from the galaxy, and I'm going to use that to take continuous pictures of a star. And so the star I want to go for is this one, if it'll allow me to select it. There we go. And so hopefully I'll be able to find that star in the view of this camera, and then use a program called an autoguider, which is going to see if stuff jiggles around. So if during the night something like that happens, the telescope isn't exactly steady, then this camera will notice that. It'll notice this star moving around. And so it can send some signals to the telescope to move it back again, to try and keep this moving around to a minimum. And that's how I'm going to keep the telescope steady for 4 hours. At least that's the plan. Now let's see if that works. So this is what we're going to go for. All right, this is just, you know, for you to understand the situation that we're going through in this simulated program, which is called Solarium. So let's go back to the actual software for the telescope. All right, so first of all, let's go and see if we can find our galaxy. So let's go now. The Sunflower Galaxy is known as a Messier-63 because I don't think this program knows the nickname Sunflower Galaxy, but it is M63. All right, so let him slew over there. So if you watch the telescope, I didn't change the view, did I? Silly me. Yeah, let me show you what's going on. There we go. Okay, so I've moved the telescope to the galaxy, and actually you can see it. Look, that's it. At least that's the core of the galaxy. And because we fixed on our on Alkaid first, we got the telescope aligned, and so we're actually in a good position. Now, for whatever reason, this camera is flipping left to right. So let's flip that back again. There we go. I think that's the right orientation. See, there's this hook of 3 stars to the side there, and so if you compare that with what we had in Stellarium, where's my Stellarium? Here it is. So in Stellarium, you'll see that's these 3 stars here, which I'm seeing in my camera. So that's good news. And there's a really bright star here, which I should also be able to find easily. All right, so let's go back to this view, and that's what our camera is seeing right now. There we go. Okay, yeah, there's our bright star. Okay, well that looks pretty good. So let's see if we can find that guide star in the second camera using the guide program. And so the guide program is called PHD, which literally means push here dummy, because as you can imagine, auto guiding, as this technique is called, of using a second camera to track a star, seems very magical and complicated, and it scared off a lot of astrophotographers for a very long time, and the software was really annoying to use, and so someone decided to write this program, and to make sure everybody believed that it would be easy to use, they called it push here dummy, which is PHD. Now it doesn't quite live up to that reputation. You have to push several times, but you can get the hang of it. It's not impossible to learn. Let's put it that way. So let's connect all our stuff. Okay. Let's see what kind of gain we have here. Camera gain is at maximum. Very good. So let's see what this camera can see. Oh, look at that. There's a guide star. Isn't that good news? Okay, well, we're in business. So let's move it a little bit. So I'm going to move the mount now very slightly to try and get this star further in the middle of the field of view of this camera. So let's I don't know, let's just try some movements and see. Yep, that seems to be the right way. A little bit more. Very good. So there's our star. So what I want to do now is I want to tell this guiding program, it needs to know when this star moves. You can actually see it moving a little bit right now in this camera view. And so when it moves, this program needs to know how many degrees or parts of a degree, fractions of a degree that corresponds to, so that it can make corrections. And that's called calibration. So we need to calibrate. So let's do that. And so what it's going to do is it's going to deliberately move the mount around and hope to detect movement of the guide star, which it is. So as you can see, the guide star is moving in that direction, and so apparently when it gives the guided pulses, which it's giving right now, it's detected that that's the movement of the star. And that will help it later on, when it detects movement in the star, to know exactly how much it needs to countersteer the telescope. Almost there. That's it. Okay, now he's going to move back a bit faster, hopefully. And so now it's been moving on the what's called the right ascension axis, which is this axis. And so now it's going to make some movements in that axis and see how it moves. So yeah, it's moving north, what it calls north now. Unfortunately, there's always something that goes wrong. So we're talking about minuscule movements right now. We're talking about fractions of degrees, fractions of arc seconds even, that it's moving the telescope to detect the movement of this pretty faint star. And so what happens is the gears in this mount, they're not exactly touching. There's a little bit of give, what we call backlash. And so since I moved the star up in what it considers to be the south direction, I've actually, when it starts moving the other way, nothing happens for a long time. And that's the problem it's finding right now. So it's moved 30 steps and nothing's happened. So this is not going to work. What we need to do is clear the backlash. And so we'll move south again a bit. Oh, need to continue looping. There we go. Let's move south again. Somewhere up there. And then we'll manually clear the backlash by forcing the mount to move a little bit north. There we go. Did that move? Didn't move, did it? There. And if we now try the calibration, you shouldn't have such a rough time. Fortunately, he's going to have to do the east-west calibration again first. Daniel Fernandez, yeah, you can use photos from my profile. It would be nice if you mentioned that I made them. And hopefully we'll get a nice picture of the sunflower galaxy after this exercise. Hi Maxim. Okay, so the east-west calibration is done. And now let's see if our clearing of the north-south backlash was successful. So yeah, see, now he's giving the telescope north guide commands, and the star is actually moving because we cleared that backlash by forcing it to move that way, and now the autoguider is moving it in the same direction and is actually causing the telescope to move, which causes the star to move. So this is going to work a lot better. And that's it. Now he needs to move back over to the middle. of course here when he's moving south we're getting that same problem. We're getting that backlash again because it's just moved the telescope over that way, and now it started moving that way and determined nothing happened. But that's not a problem because it's done its calibration. It only does its calibration in one direction. So it's telling us it didn't find any south movement, but that's because unfortunately we have a lot of backlash. So this doesn't matter. This is fine. The only thing we want to do is, since we've been moving around this guide star a lot, our galaxy probably isn't exactly centered in the field of view anymore. So I'm going to stop guiding and continue looping and first get our galaxy centered. So let's go back to our main imaging camera, which is this one. So if I take another preview, let's take a 3-second one, or 2-second, then probably the galaxy won't be exactly in the middle anymore. Actually, it's not too bad. Let's just, tell him to go and center it. And while he's doing that, let's watch carefully what happens to the guide star. Not much, actually. That's good news. So we didn't move too far off, which is great news. Yeah, he's just making sure that he knows where he is. Okay. So finished, and there we are, and there's the galaxy. In fact, I can show you exactly the result and plot the DSO. Yep. Exactly where. So the galaxy is about that big. Thing is, because we're taking a really short exposure, let me turn that off again. Take another preview. We can really only see the center, the nucleus of the galaxy, because that's the brightest part of it. And so the rest of it we're gonna only see once we start taking much longer exposure photographs. So this here, which you can see right now, that's just the nucleus of the galaxy. But that's enough to, get oriented and get stuff. So now we can start guiding. This is the fun part. So let's turn on the autoguider. And so now it's tracking what's happening to the guide star in this camera. And if it detects the star moving around, which is what these red and blue lines indicate, I need to change a few settings. So can we go with half a second? See, this is how clear a lock it has on the star, and that actually looks reasonable. So let's go with half. Here's the backlash problem. See that? So it's moving the telescope frantically in the opposite direction, and nothing's happening. And we'll let him settle down first before we start taking pictures. You can see how well he's doing on this graph here. So this is where we want to be, and this is where the star actually is, and you can see it's drifting down because of this backlash problem. What information is that, Maxim? Okay, and so now the gears have caught up, and so you should hopefully be in a better position. Yeah, and so now we're guiding. We want to get it, if we can, within 1 arc second. That's about the resolution of that camera. So the pixels on that camera, the distance between 2 pixels, is about 1 arc second. So it's half one of these divisions, or it's this circle. So if we can keep the guiding within that circle, then we'll be alright. And it looks like that will be possible. Good. Let's get started. So now we can take some real images. So let's take 3 minutes. That's 180 seconds. Let's move the. So gain on this camera is if you have a DSLR, that would be the ISO setting. So it's how much you're amplifying the raw signal, the raw electrical signal. And as with digital daytime photography, you want to keep that as low as possible, because this amplification only generates noise, and you definitely don't want that. So let's keep this down to 250, and let's see what kind of sub we get. So let's do just one, and now we wait and try and keep very still for 3 minutes. let's watch how the guiding is doing. See, it seems to be doing alright. So we're pretty much within 1 arc second, which is good. Yep. How much longer do we have to wait? So that's 1 minute, 2 more. So what we're going to do is we're not going to take a single exposure of 4 hours. We're going to take many 3-minute pictures, 4 hours worth of 3-minute pictures. So 3 minutes, you can do 20 in an hour. So we'll hopefully have 80 pictures, all of them 3 minutes long. And when we have all those pictures, we'll combine them all together, make the averages, and try and bring the noise levels down. And then we'll have a better chance of seeing the details in the galaxy. You won't see them in a single 3-minute picture. You'll see some of the levels, but it will be very noisy. So we'll see that in a little bit. In 1 minute and 17 seconds to be exact. But so that's the technique that we're going to use. We're going to use 3-minute pictures, and we're going to use 4 hours worth of them. Less than a minute now. How's the guiding? It's the perpetual bane of the oh, it's pretty good actually. It's almost within half an arc second. So it even sometimes, in fact now it seems to be the case that there is more of an error in that direction than there is in the up-down direction. So the up-down direction is that way. And the left-right direction is that way, and this is the direction of rotation of the Earth. So that motor is actually continuously turning the telescope, and so the error, this blue line or this left-right direction, that's the error in the rate of turn of that motor. And the red line, we call that declination. That's this up-down direction. That tells me the error in my polar alignment. So if I'm not exactly pointed at the North Pole, then at some point, when I turn around the wrong axis, the star is going to move up or down. And since that's not happening, that's actually a pretty good sign that I did a good job of my polar alignment. Alright, we should have our first, yeah, there it is. So we have our first sub. Now, again, not terribly much detail visible here, but let's push up some levels. So yeah, there you can see there's some light here for the rest of the galaxy. Can we push it even further? Remember, this is a single, but it's definitely there. You can see it's a flocculent galaxy, M63, or the sunflower, which is where the name comes from, sunflower. So it looks like it has a bright center, and then it has all these little bits of cotton wool, like the seeds of a sunflower, all around of it. And you can actually see that here, which is pretty good. Can we go even further? Now I'm obviously overdoing it because this is just 3 minutes and we need 4 hours worth of pictures to get a good view, but that looks pretty good actually. So we're just gonna carry on like that. So let's move it back to its default level, and let's do some more. Let's do an hour's worth. So we have 1, so we need another 19. There we go. Now one other thing that I want to do. Here, this is the view that comes from this camera. This camera is cooled, so there's a cooler in the back here, which is reducing the temperature of the sensor. Now it's pretty cold here. It's maybe about 6 or 7 degrees centigrade, positive. But I've cooled the camera way down to -20, and that's going to give us even less noise. Now, what was I going to say about cooling the camera? Oh yes, even though we're doing that, the sensor in here is as good as it can get with that low temperature, but there are still manufacturing defects. Like some of the pixels will be a little bit more sensitive than other ones. And so because I'm using auto-guiding, I'm forcing the galaxy to be at exactly the same pixels on every one of my 3-minute pictures. And so each one of them, if there's a defect in one of the pixels, then each one of my 3-minute pictures is going to have that same defect at the same place in the galaxy, and so it's going to look like there's something wrong with the galaxy. So what I want to do is, in between each 3-minute frame, or in between not each frame, but maybe every 3 or 4 frames, something like that, I want to slightly move. So I want this auto guider to automatically move in some random direction to make sure that the galaxy is not exactly at the same place, so that I can smear out any deficiencies in the pixels of that camera. That operation is called dithering. It has an official name. I think it was invented for the Hubble Space Telescope initially, but now it's available to us amateur astronomers. So dithering is actually very simple. I need to just connect this camera software with the auto guider, which I can just do here. So it tells me that the auto guider is guiding, and when I've done that, I can tell it, let's say every 3 frames, to send a dither command to the auto guider, and that will slightly move the telescope, but it's a few pixels, no more, so it's almost undetectable by the human eye, but it will move it ever so slightly, and then that way try and smear out any problems with the camera. Alright, so that's going pretty well. So there's this tradition in astronomy, once you start getting what we call light frames, data frames like these, there's not much left to do. You just have to wait for 4 hours. So I think it's time for a drink. What do you guys think? Cheers. As you can tell, astronomy is a waiting game. I think we'll carry on until we get the first dither, so you can have a look at that. But then after that, there's not much left to do, so I think I'll go inside at some point and do something else. Maybe work on some old pictures while these are being taken. There's our second frame. Looks an awful lot like the first frame. Yep, there's the galaxy. You know what that is? That's not some wormhole in space. That's a bit of dust on my camera sensor. Fortunately, I had a good look at the sensor before I screwed it into the telescope, but apparently I still missed one bit of dust here. But fortunately it's far away from the galaxy, and we're at the end in the morning. I'm going to take what are called flat frames, and the flat frames are frames against a completely white background, usually the dawn sky. And so this kind of deficiency will show up, because I'm not going to touch that camera or move it at all, and so that will show up. And so what the processing software will do afterwards is it will subtract these deficiencies in the what's called the flat field, so that hopefully we'll be left with just the galaxy and the stars. Starting to show up even better now. That's probably because it's still getting dark. It's not totally dark yet, and so this quality will keep increasing. This blue here, this background, is indirectly light pollution. So that's all of the city lights everywhere in Berlin, which is shining straight up into the sky and scattering off the air molecules. I have a filter in the camera which reduces a lot of the yellow and red wavelengths of light pollution, but not the blue ones. And so we're left with a blue sky, even though it's actually completely dark. But trust me, this is a lot better than if I didn't have a filter in there. If I didn't have a filter, this would be completely white. And, so that's how I get around the light pollution here in the city. And in post-processing, we'll readjust the color balance, and we'll bring down the dark levels of the background sky so that we get it black. So there's still a bit of trickery that we can use in our picture processing software afterwards. All right, here we're getting a worrying message. I'll talk about that in a minute. Let's just look at this frame here. There's that one. Okay, that one was a little bit brighter. Maybe so there aren't really clouds, but there might be, you know, little bits of air which are slightly more moist or slightly less moist, and so they'll reflect more or less of the light pollution, and so the background does vary slightly in brightness during the night. Okay, now let's deal with this saturated stars here. So we need to go to the auto guider, which is here. So we're at 50. We should probably be closer to 40. So here is something interesting. See that the average is kind of leaning towards that direction, so maybe my polar alignment was not as perfect as I thought. But it's alright, the guider can deal with it, and we're staying pretty much. So these kind of shadows, those are the corrections, so I can turn them off. So you can see the actual movement of the star. And so the actual movement of the star is, barring a few exceptions, almost within 1 arcsecond. It's actually better, it's within half an arcsecond. So that's pretty good. And it's better in declination than in, so declination is up, down, than in right ascension. And right ascension is the rotation direction of the Earth. Okay. Now, yes, saturated star. So what we'll do is we'll bring the gain down on this camera so that there's less noise and so that we don't saturate the star image, and that will give the auto guider a better opportunity to judge exactly where the star is. And so let's bring that down maybe to 90%, something like that. See if that makes things better. So does that get us closer to 40? No. It's lost the star. Yeah, so we don't want to do that. Let's keep it at 100. And I think we'll take 1 second exposures, because this is a very faint star. And now we'll definitely get saturation. And so now we can reduce the gain. How are we doing? Yeah. Let's just see what happens. So when people go fishing, Kasha, do they also drink when they've caught a fish? I didn't know that. I've never gone fishing myself. So, yeah, that's when we. So let's just watch this. See if we get this error anymore. This saturated star. I actually think the signal's getting stronger, which would be consistent with the sky getting darker. Let's change that back to the full histogram. Yeah, I think that background is getting darker, which is good. That's what we want. Okay, this is exciting, guys. So we seem to have taken care of this. Look. So yeah, we missed the dithering. Maybe we can still see it. So here is a dither command, which was sent by this camera control program. So we told it to dither every 3 frames. So that's every 9 minutes, because each of these is 3 minutes. And so it sent a command here to the auto guider. And so what the auto guider did is it moved the position where it wants to be. So these 2 green lines, it chose some random movement of a few pixels. and then try to get the guide star into that new position. And so the effect of that is to slightly move the position of the galaxy on this camera, because these are totally rigid with respect to each other. This thing here, this is called an off-axis guider, and it's rigidly screwed in a very specific orientation, and this won't move. So these two cameras they're glued together essentially. So any movement in here is reflected by movement in the camera, which is recording the galaxy. All right. So if all of that, look at this. This is brilliant guiding. That's less than half an arc second. Okay. Well, there's no wind, so that's a good sign. Which means the stars are pretty... I guess you can't see them from the camera, it's much too dark. But of course you can see them with the naked eye. Anyone who's in Berlin, just look out and you should see a very clear night. Good. Okay, so let me quickly show you final picture of what we hope the galaxy will look like when we're finished. I think there's a picture in Stellarium, that's simulation program. Where is it? Here it is. Yeah. So that's what we're going for. So we can kind of see that, right? So we definitely have this center of the galaxy here, this nucleus, and we could see a little bit of this stuff going on. What we can't see yet, but we'll see that in the final image, is this bottom half of the galaxy is actually quite a bit darker than that side, and so all this brown stuff here, this is dust, smoke actually, which is lying on top of the galaxy. And because the galaxy is kind of, so it's over there, it's in that direction, but it's slightly tilted like this, and so it's the side closest to Earth is the one which is facing away from the North Pole, which is this one. All right, I think that's it, guys. It's running, and so we'll bump this up. So we want 4 hours. In fact, it will tell me here. Yeah, I have 3 hours until it crosses the meridian, which means it'll be exactly there, and then I can do another hour before it disappears behind my apartment. So yeah, we can do 4 hours, and so we should add another 60 to that, and so that should be 79. Yeah, so I think I'm gonna leave it here, and I hope you enjoyed watching me. I can't believe how well everything went. We got everything set up and we're actually imaging. Usually when you do this stuff live, everything goes wrong and you can't find the star, and things are out of focus, and the cameras don't connect, and everything's going much too well right now. So I think I'll just drink some more and not think about it. And I will get back to you when the image is processed and let you know if we got a good image of the Sunflower Galaxy. Do you want to have a quick look at our imaging results and then leave you with that? So there we go. And let's have a look at the compress the histogram so we see the relevant parts. Yeah. So you can see now this is overexposed because this is a very crude image processing. So when I actually process the image properly, I'll obviously try and not brighten the center that much and keep that to its normal level, so that we get a more appealing picture. Alright guys, enjoy the rest of the night, and let's hope that we get a good picture of the Sunflower Galaxy. Alright, so here we are on the next day. In the end I was able to capture 5 hours worth of 3-minute pictures, so that's 100 pictures in total. And after processing those, we get this resulting image of the Sunflower Galaxy.